Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, I'm pleased to introduce Ethan Jackson from the Vanderbilt University in Nashville. So typically he speaks to people in embedded system designs and audiences like that. So his institute is involved in an interesting corner in which touches on control engineering, system engineering, and software engineering. And in general, what they do, they use model-based design, develop model-based design, apply model-based design, prove correctness of model-based designs, and things like that. So I asked him not to tell us at once all what he has in his thesis. Hopefully he'll come back and continue. So today he will give a more or less introductory talk to what he's doing. Welcome.
Great, thank you so much. So as Dr. Gurovich mentioned, we do model-based design, and I just want to start because I think that model-based is quite a general term. So I just want to sort of narrow the focus about what we look at with model-based design, which is what are the core principles that make it work? What are the key ideas that allow it to work in so many different areas? And my research is on how do you sort of formalize these ideas? How do you build general tools that allow you to apply it in many different domains? So I want to begin by looking at the challenges of modern, I think this word is an inconvenient word, modern system design. I just use it because there are so many different sorts of systems out there that can make use of model-based approaches. But they have some things in common. They tend to be very heterogeneous. They tend to have non-functional requirements that really have to do with complex dynamics of the system, dynamics over time and space. And they're usually resource constrained, especially in embedded systems. Then I want to talk about what are the key ideas in the model-based approach for system design. And I want to look at some detail on a particular domain, the domain of synchronous reactive systems, where we take these key ideas and apply them here and produce a tool set for designing synchronous reactive systems, but gaining the benefits of the model-based approach. And then I'll conclude with some research directions. So the first part will be sort of introductory. So modern systems, what's interesting about them is that they really span size and functionality. You can't pin them down by just saying they're distributed. You can't pin them down by just saying they're embedded. Some classical examples are you have, let's say, the cell processor, which is coming out. It's square millimeters in size. Nonetheless, it's very heterogeneous, has all the properties of a modern system. You have embedded systems like you find in a car, which are really miniaturized networks that have to be safety critical. They have to interact with the complex dynamics of the environment. And then you have global, massively distributed systems that are sort of data-centric. They distribute data and content. All of these have these fundamental things in common that you can't really view them anymore as a sequential system. You have to view them as a set of concurrent interacting entities. There's a bunch of them. You have to understand how they interact and that sort of stuff. So just to go into a little more detail, let's take the cell processor. If you look at it, it has heterogeneity, and that on this single chip is a whole bunch of different things. There's a PPE, which is basically a power PC embedded on it. Then there's 8 synergistic processing elements, each of which supports different functionality than the PPE. They focus on vector operations, mainly for graphics. And then you have a complex interconnect bus to link all of these SPEs to the power PC. These 8 individual units can't directly access memory. They have to do it through this interconnect bus. So you get some interesting dynamics here. How can these things access memory? how does the PowerPC schedule processes onto these SPEs to use the cell processor efficiently? And of course, there are resource constraints. Not all of these things can talk to memory at the same time. They have to go through this same bus. What's interesting about the cell processor is that it really now puts into the forefront that traditional software design can't escape these sort of heterogeneous systems. If you want to really get the power out of this thing, you have to figure out how do you make software run faster on an architecture like this. Now let's go up in scale a little bit and look inside your car. And there you find about 80 processors made by different vendors who don't have strong specifications about what exactly their processors have to do. They have some functional requirements, but essentially each one is a black box, and the automotive company has to figure out how to put these black boxes together. Not so easy. They run on different sorts of bus architectures with different temporal dynamics. So CAN bus, FlexRay, these are based on time trigger communication. And the control systems on a car have to deal with the sorts of hybrid and continuous dynamics imposed by a physical reality. So if the car is to apply an analog brake in a meaningful way, it needs to understand the physics about what happens when this brake is applied on a bunch of snow, for example. It does this, of course, with sensors that sense the environment. These signals come back in, they're discretized, they're put into a discrete system that now has a discrete view of the world. It produces an actuator, it produces signals to an actuator that affect the continuous world. So there's a very complex dynamics here that involves both continuous and discrete. And of course, there are also resource constraints, mainly in terms of power and the amount of data you can communicate. Let's go up one scale further. There's lots of examples I could have picked for massively distributed systems, but some common ones are, let's say, your instant messaging, your favorite instant messaging client, which I assume is Microsoft's. And if you look at the biggest one, let's say AIM from AOL, it boasts 60 million users. So the heterogeneity here is in terms of the number of nodes and the different sorts of nodes that this software runs on. It runs on phones, it runs on Macs, PCs, Java-based platforms. So there's a lot of heterogeneity. And there's dynamics too, really interesting global systemic dynamics. When does the system lag? When does it bottleneck? How can it be completely connected? There are also resource constraints. Distributed guys usually phrase these in terms of quality of service, but they're really constraints on resource, which is how you get data through the network. Latency, throughput, reliability, and most recently, security. And there's another interesting example that's been in the news, which is this Second Life massively multiplayer game where you go on, you interact with, I guess now it's up to about 2 million users, 60,000 of which are usually online at a time, somewhere around that. So, so you can see that. Whoa, what did I just do? I hit a bad button. Okay, so you can see that that modern systems really span size, they span functionality, but they sort of have some common threads. And the model-based approach to system design tries to deal with this commonality that systems have heterogeneity, resource constraints, and complex dynamics. Now there are several key ideas, and the first one I want to talk about is the notion of a domain-specific language. So the first key idea is that these systems are too diverse to capture them with one modeling tool. You can't require everybody to think about their systems in terms of C++ because it's not necessarily the most natural way. Threads are not the most natural concurrency model for every system. So the model-based approach says, okay, let's not require every system to be designed with the same underlying concepts, but allow a system to be a system designer to specify the precise domain in which they plan to design. And they do this by constructing what we call a domain-specific modeling language, or a DSML. A DSML has two parts to it. The first part is called the structural semantics. And the structural semantics identifies the sort of structures that you use to describe to architect systems. So a common structure here might be a data flow graph like this. This is very convenient in, let's say, the embedded systems world. And the structural semantics lets you identify which of these pictures are good and which ones are bad, which ones have errors in them and which ones don't. And it does nothing more than that. So From the structural semantics, a model is just a mathematical structure with some rules on its construction. Now, of course, this is not enough to specify all the properties of a domain. You need to specify what these structures mean. And we call this the behavioral semantics or the operational semantics. There's a bunch of different terms. But basically, you want to explain how this diagram induces some interesting meaning. So a very simple example of this diagram might be to say, well, each of these blocks represents a function, some n-ary function, over some value domain. These connections are just projection operators. They pick one value from some tuple of outputs, and they project one onto the input of another function. And then the meaning of this total diagram is recovered by just composing all of these functions together. So that would be one way to attach a semantics to this structure. Again, it's important to be precise about these things because if you look over on the little sidebar there, you see an example where one line is driving two inputs. And under this interpretation, that would give you a semantically meaningless composition of functions because I didn't tell you how to compose values. Okay, so that's the theoretical picture. Now, how do you actually do this in tools? The way that you do this in tools that support the rapid construction of domain-specific modeling languages is to first give a way to define the structures. What are the objects that represent your systems? And we call this meta-modeling. And the meta-modeling tool developed at Vanderbilt is called the generic modeling environment. It has a language based off of UML. UML class diagrams specifically. And these diagrams allow you to describe the structures that are interesting to your domain. There's just a couple essential concepts. I'm sure many of you have seen UML before. You can identify a class. You can identify inheritance relationships between classes. You can say that one class contains another with a containment relationship. You can say that some classes are related by associations. And associations are essentially some sort of typed edge between two other classes. Okay, so you have a very simple way to describe the relationship between the structures that make your domain. And then you build a meta-model. This meta-model describes sort of an automata-based language. You construct this meta-model in GME. GME interprets this meta-model and then generates for you a modeling environment that lets you construct domain models. So for example, this one describes, I'm not sure how easy you can see from back there, but this one describes a hierarchical finite state machine. So you have things like compound state and primitive state. These are inherit from some state base. States can be connected by transitions. Here, transitions have triggers, guards, actions. So you specify all this information, you just give it to the tool, and then out pops a modeling environment that lets you build hierarchical finite state machines. So it gives an interpretation to this picture, and then you can construct your models. So it's a pretty nice way to at least get the first shot at a domain-specific language, which is this structural part. Now the harder part is always this. How do you get the behavioral semantics? How do you attach in a fast but reliable way meaning to these pictures? And the GME tools provide different ways to do this. This is still ongoing research. Sort of the programmer's model is that what the tool provides you is a representation of your model as some sort of abstract syntax tree. Tree here is not really accurate because it's more of a general directed graph. And it provides you with a set of APIs and a COM layer so that you can attach a program that reads through this model and does something with it. So if we're talking about a hierarchical finite state machine, your program might read in this automata as it's represented by this abstract syntax tree, and it might generate out C code, for example, that simulates it. Or it might directly simulate that model and let you feed in some input or something like this. And then that program represents the behavioral semantics of this domain. Now, the difficulty with this approach, it's definitely flexible, but it gives you the same sort of problems that have been leveraged about, let's say, Simulink and Stateflow from MathWorks, which is that you have a very complicated language, and its meaning is buried inside of a very complicated C program. So as a modeler, you don't have sort of a nice, elegant, simple way of saying what exactly does this mean. What exactly does an arrow crossing hierarchy mean in a hierarchical finite state machine? So the danger here is that you don't provide somebody using the language to build models a way to exactly understand clearly what the semantics of the model are. So the next shot at this was to say, well, if you look at an example like hierarchical state machines, you can define its semantics in terms of state machines that aren't hierarchical. And you do that by providing a composition operator that takes all of the concurrent state machines and it composes them together into one big automaton. And then that automaton has a simpler semantics. It has no hierarchy, it has no concurrency. You just evaluate the guards and walk through it. So people said, well, in a lot of cases, you can just take these complex languages, you can view some of their features as syntactic sugar, if you will, and you can transform them onto a simpler language whose semantics is clearer. And the way you support this is by a graph rewriting rule that tells you how to take an input model like a hierarchical automata and rewrite it into a flattened automata. And so there's a tool called GREAT. It's the graph rewriting and transformation tool that lets you specify these graph rewriting rules. And in this way, you can link more complicated domains to simpler ones through a model transformation. And then the model editor will, of course, give you back the flattened model. So this is part of the flattened model of this hierarchical automata here. And then once you have a simpler one, then you may say, well, it's simple enough now that people won't worry about what the C code does, so now we'll give it to the code generator. Now, even at this point, you still have the problem that a lot of semantics can't be completely specified transformationally. You need more complicated things than just transformations over model structure. So the latest work terms semantic anchoring. I don't know why that meshed up a little bit. Term semantic anchoring is to combine graph transformations, which is a very nice way of relating structures, with ASM developed here, which is a very clear way of specifying an abstract program. So the idea then is that ASML is used, Spec Explorer is used to capture the behavioral semantics. For example, how do you execute a state machine? It's very concise. It doesn't involve the details of pointer arithmetic, memory management that you get at C++. And then you link this with graph rewriting rules so that you take a complex language, boil it down to a simpler structure, generate from this simpler structure a data model in ASML, and then just concatenate that with the semantics of state machines, for example, written in ASML, and then you can simulate and generate test cases and this sort of stuff. So this is a picture of the work that's been going on about for the last 12 years now in how do you attach behavioral semantics to structure, to the structural semantics. Okay. So once you can do that, once you can build these domain-specific languages, you can now link them together in some really interesting ways. So let's say you start off with this one up here, that you want a rough view of your system as just a bunch of functional blocks connected together. This is a common way of thinking about the architecture of a system. Well, you can say, I can attach some meaning to this as a composition of functions. And if you view it as a composition of functions, then actually you can say that there should exist some unique fixed point, some least fixed point, which is the end-to-end simulation of this system for a given set of inputs. So you feed some inputs in, you let the system run, it reaches a fixed point, which hopefully is the least fixed point. And then this tells you what this architectural view should do for a particular set of inputs. And you get a very simple and nice way to think about the system. But now it comes time to say that these blocks, for example, are concurrent. They can run concurrently. And this model here doesn't capture that concurrency. So what you do is you build another domain-specific language, let's say something based on synchronous data flow graphs, where you map this less detailed architectural model onto this more detailed synchronous data flow graph that now talks about concurrency. And once you do that, you can ask some interesting questions. Does there exist any deadlock, for example, in the system? you can do deadlock analysis here. Where up here, it didn't make any sense to do deadlock analysis because the semantics were too simple. Now, you might look at this and say, well, there's no deadlock. It's pretty good. But the problem here is that the SDF model has no notion of time. You didn't say how long these computations took. So then you may do another mapping onto another domain-specific language, let's say timed automata. This is a screenshot from Upal. So you can translate this data flow graph onto a timed automata model where you can now verify any TCTL formula. So the idea is that you can link these languages in what people call a platform stack, where you start out with a very broad, simple semantics, and you incrementally refine the system. Each refinement allows you to be more specific about what the model means, but each refinement increases the complexity, so it becomes harder to do verification. The idea, though, is that when you build this whole stack, you can sort of move down the complexity level, or move up, as is the case, and you get a picture of what your system means at sort of different snapshots. Yeah?
So regarding complexity from the usage of this approach, how do you define the platform mapping?
Yeah, the platform mapping is a tricky thing to define, and in fact, this is a whole research area by Alberto Sangiovanni Vincentelli at UC Berkeley with his tool Metropolis. The way that we try to define platform mappings is with graph transformations. So in this example, you can see that it's fairly easy to get a graph transformation from here onto a structure like this. From here onto a timed automaton model, it's not so hard. You sort of, for each data flow element, you...
So is the user going to define this mapping, or do you do it generically?
Oh, I see your question. Yeah, so what happens is that whoever develops this platform develops these mappings. And then once that's done one time, then users who develop systems on your platform can reuse your languages and your mappings. So this is one thing that we're trying to do right now at Vanderbilt, is to build a canonical set of these things with all of these mappings and all of these domains pre-built for you so that you don't have to worry about how to do it.
Sorry to ask again, I mean,
yeah.
In the first step, for example, you add some information somehow for the particular instance on this platform, right? I mean, you don't have concurrency represented on this level. So where does that additional information come from? The user still has to provide this.
Well, in this particular example, the concurrency is built into the structure. So here you just have a structural transformation, but once you take this and you translate it onto a structure here, this structure has, via a process like this, some concurrent model of that system. Now the question becomes, does this really the more difficult question is, does this platform mapping that takes a model here to a model here, does it do this in a correct way? Does it produce a more detailed model that sort of keeps invariant the things that you had here? And it turns out that this is also a very difficult question to answer. It's called refinement verification, and this is a whole other branch of research to figure out, did you build a platform mapping so that the results here accurately reflect this more abstract system? Okay, so the idea of platform stacks was to give you an incremental way to introduce the essential complexity into the system. Now, a lot of systems need more than one platform stack, unfortunately. There are so many different aspects to system design that you can't just build one single DSML to represent all of the concepts in that system. A typical example might be that you can partition a particular class of systems into some deployment language, some language for defining the functionality, some language for defining the timing. I could add here a language for defining the security model. So there are all sorts of semi-orthogonal information that you need to specify the system. And the final key concept in model-based design is to split this information up into individual domain-specific languages so that you can specify the system in separate views, and then to give a way to compose all of these views together to get the whole system out. Again, as you can imagine, this is not an easy thing to do. It involves composing structure. This is pretty much worked out now. The harder thing is composing semantics, these domain-specific semantics. Also, you can imagine that Let's say you make some decision about how to schedule components in a system. This will have influence on what is the optimal way to decompose the functionality. So though you divide the system into these individual views, the views interact with each other. And this also has to be accounted for. Engineers need to have some mechanism to keep track of how these views interact, so that an optimal local decision isn't an awful global decision. So putting all of these things together, these are sort of the key concepts in the model-based approach to system design. Capture the domain, use platform stacks to slowly, incrementally introduce the essential complexity. And then when your domain is too complex, partition it. Use a divide and conquer approach, partition it into smaller domains. Maybe I should stop here and ask if there are any questions on this general approach. Feel free to interrupt me at any time, please.
So could a lot of this be declarative, or do they really need to be languages in each of these different levels?
Well, I guess, so when you say declarative, I think from my view, what declarative means is in what way do you define these semantics? So in my view, a declarative style is saying how would you like to define domain-specific semantics. I think it's incorporated into this framework without any problem or argument, I guess. So in this example, this is what we've been working on, abstract state machines. But you could do this with some convenient declarative language if you wanted to as well. I think there would be no contradiction there. Yeah. So these concepts are I think are good concepts, but of course the devil is always in the details. And so when can you apply these to get some strong benefit? And in this next part of the presentation, which is a little more tedious, this is a case study that I did for about a year, where I looked at a particular mathematical model for a class of systems called synchronous reactive systems. And I tried to reformulate this class using these model-based approaches and develop a whole model-based framework that really shows you get benefit from partitioning a system in this way, from creating these different domain-specific modeling languages. So let me give a bit of a background on synchronous reactive systems. This is a fairly well-studied class of systems, used a lot in embedded systems. It came from some French mathematicians, Gérard Berry and Paul Caspy, initially. And the basic model is that let's assume the things in the components that you build run much faster than the environment interacts with them. In fact, they run so much faster, you can assume that their computation time is 0. It's negligible. In this case, you might see the system like this. At some point in time, you kick the system with some input, and it instantaneously produces some output. Okay, then there's some time passes. The system gets kicked again, produces some input, instantaneously produces the output. So what you get actually is you get a timeline that's not discrete. It happened at specific times. But since the computation takes 0 time, there's nothing else interesting that happens after that point where you kick the system. What it means is that you can discretize this timeline. You can find a mapping from these timestamps to the integers that gives you a discrete version of the times at which the system reacts. And so you can just number these: the first reaction, the second reaction, the third reaction. Of course, at each reaction, you zoom into it, and you find there an entire system that responded to these inputs. Okay. Now, the tricky thing, the trickiest thing perhaps about the synchronous reactive model is that even though you imagine this automata, for example, to execute in 0 time, there are still causal relationships between things that have to be maintained. So let's say that inside this automaton you found something like this, these two concurrent automata. What this one says is that when the system is kicked with an event E1, this automaton will emit a B if it sees an A. And similarly, this automaton says if I'm kicked with an E1, I'll emit an A if I see a B. In the synchronous terminology, this would be called a causality violation, because if the system ever could do anything, if it could emit a B or an A, it would imply that, let's say the system emitted a B, it would imply that this B went back in time, actually, and it would imply that this A went back in time to be observed by this automaton at that discrete instant in time. So the tricky thing is that even though you imagine the system to take 0 time, there's still a causal ordering within the program that has to be maintained. And this is called causality analysis in the synchronous language literature, but it's pretty much like deadlock analysis. Like I said, this model has been around for a long time. There's many different implementations. Esterel is the automata-based one by Gerard Berry. Uses an automata-like interface called sync charts. It's similar to state charts. There's Luce by Paul Caspi, and then Signal by Albert Benvenice's group. Okay, so again, I said the devil's in the details. Before I can tell you how we approach this problem, we have to get into a little more detail what exactly this synchronous system is. I picked the Signal model because we worked with the Signal guys on this. The Signal language is very simple. It has only 5 constructs. So let me just explain these constructs. You can write in the language that some value z is equal to x, some operation y. So z equals x plus y, for example. This has the obvious meaning that each time the system is kicked, each time an event happens, you calculate z to be whatever x is now plus whatever y is now. So this is said here that for all instances k, for all points when the system is kicked, you calculate the next value. Now the trickier thing is that when a system gets hit with some events, not all of them might be there. Some might be missing. And what all of these synchronous languages do is they extend the values that a variable can take with something called absent. And it's represented with this bottom symbol here. And absent means that there's no value. At this point in time, the system was not given input on that particular line. So if you have a setting like this where z is equal to x plus y, you would have a problem if x was here but there was no y to do the addition. In fact, it's important to be careful because if you're not, you might have to queue up, you might have to store these values of x's and wait for values of y's, and then you get unbounded memory. So this simple operation imposes a constraint on when events can come into the system. It imposes a constraint that says, well, if z at this point in time when you calculate it is not absent, then it implies x and y are also not absent. So for this construct, you also get a constraint on time, on when events can happen, synchronizing all of them. Now, Signal does an analysis to try to figure out whether your programs are right or wrong, and they do this analysis on an abstract model. Let's see. The abstract model says that along with each variable, you can associate what's called a clock. A clock says the set of instances when the variable is present, the set of instances when it's absent. So if you have something z equals x plus y, what it says is that all the variables have to be present at the same time. All of their clocks have to be equal. And the value of variable z depends on knowing the values of variable x and y. So this is a causal relationship. Okay, these other ones will be faster. State in a language, in a data flow language like Signal, is usually represented by a delay. That is, you can remember a value from a previous point in time. This expression here says that y is the previous value of x, the past instant. And the constraint on y is that its value is equal to, its value at instant k is equal to the value of x at k minus 1. And if y is not absent, that implies that x is not absent. It should be if and only if, actually. Okay, you can undersample a system. Undersampling means that you're kicking the system at some rate, and you only take a subset of those kicks. So you can say that you have a variable x, and it's equal to u only when some Boolean constraint b holds. So you take a subset of the times that u is come based on this b. This is a little more complicated. You say that x equals u when b is true. Otherwise, x is absent. And the abstraction is that the clock of x is equal to the clock of u only when b holds, and x is causally dependent on b. X is causally dependent on u only when b holds. Okay? And then there's one more interesting one, which is the merging of two signals. So this says that x can take on the value u if u is present. If it's not present, give it the value v. Okay, so this is set here. In this case, the clock of x is the union of these two clocks. The event when u and v are present, you union all of those times together. That's the events. Those are the times when x is present. And x is causally dependent on u. X is causally dependent on v only when you subtract, only at the instances when v is present but not u. Okay, so these are the simple, the four basic concepts for building synchronous systems in Signal. These are the ways they're abstracted into causal information. And now, to build a big system out of a whole bunch of these statements, you need to give a way to compose statements together. And the composition is very simple. You translate each p and q into its equations, and you just union those sets of equations. So from the synchronous reactive model, you capture events, you capture functionality, you capture scheduling with just these four constructs plus a composition mechanism. Okay. So how easy is it now to use this elegant model? It's simple. It just has a couple constructs. How easy is it to actually build something like this? It turns out it's a little bit tricky. This example here is written in Signal. And what it does is it's an alarm where you give it some order. You say, I want something to happen. I order you to do something. The alarm counts how long it takes for that order to be completed. If it's not done in time, it sounds the alarm. Okay, and it tells you how much time it actually took. Now, this simple Signal program can be translated, just its functionality, ignoring anything about scheduling, can be translated into a C program sort of like this. I did this because this is easier to read for a lot of us who know C. So it essentially means that there's some sort of loop. It's looking for done and order signals, and it's keeping track of counts and sounding the alarm at a particular point in time. Now, it also means these sets of equations over here, which link together the clocks of all the variables. It gets even more complicated because the way that I wrote this C code, actually I wrote it knowing what these clocks did. So for example, there's a clock equation here that's in bold saying that the clocks of essential key signals, order, done, and tick, are all linked. All of these clocks are linked together. The clock of the counting signal is the union of all of these. If I hadn't put that in there, I wouldn't have been able to write this. So I added this clock constraint that allows me to interpret the functionality this way. The functionality also implies equations on the clock side. So these views are intertwined. This small program really packs a big punch. It tangles together a whole bunch of different concerns that the designer needs to keep track of. Now, it might work pretty well if when you run into an error, it told you your error is that you didn't give this equation. But this isn't so easy to do because causality analysis is a global property. The way you calculate it is you take all of these equations, you try to find a triangularizable version of these equations that keeps into account all of the causality constraints. And if you find that, then you're good. You found a solution to the system. If you don't find that, then something's wrong. But what's wrong, it can't tell you because the process fails because it can't take this whole set of equations and find a reasonable interpretation for them. So you can't point to any one equation and say, that's the bad one. All right, so to me, this is a good candidate for model-based design because you already have a well-understood system. You have a semantics. The problem now is that it's hard to use the semantics because everything is so tangled together. So the next approach was, can we define a set of domain-specific languages and a simpler interaction mechanism so that you sort of get a better idea of how the functionality, the time, all of these things interplay with each other. And after a couple trips to and from France to talk with Albert, we came up with something like this. You start with a set of simple operators. Assume that there's some stateless n-ary functions like plus, whatever. You compose these together to build data flow graphs. And the semantics you give to these data flow graphs are very simple. A graph has a certain number of inputs. The component only fires when it has inputs, all of its inputs filled. And when it fires, it consumes its inputs and produces exactly one output. So it's a very simple model. It's technically called a synchronous data flow graph, homogeneous synchronous data flow graph of rate 1. But it's a very simple model. Deadlock on this model is very easy. You find a cycle, basically. You can extend this with a delay edge for memory, where this edge remembers its previous value and passes out the previous value. Okay, so there's a very simple model now that you imagine encoding the functionality. Now, what about this more complicated notion of scheduling? Well, to handle this, we defined another domain-specific language that's dependent on this model. But what it does is it defines a set of modes, a set of cases. And when a case holds true, it actually reconfigures this data flow graph in a particular way. So this one is a counter example. What it says is that, OK, let me see the best way. All right, so let me say a little bit more about what these modes are. Each of these modes represents a particular case, a particular response of the system. And each mode has constraints on when you're allowed to apply it. And this color coding actually represents these constraints. So when the inputs are black, it means that you can only apply this mode if you kick the system in such a way that you didn't give it any inputs here. These inputs are absent. If the inputs are white, it means that you need to have input on that signal. If they're X'd out, it means you don't care. It can either be there or it cannot be there. OK, so in this simple example, let's say that you didn't, this counter has a reset and a count signal. Let's say that you didn't provide it any reset and you didn't provide it any count. Then the color coding here of black means that you reconfigure this graph by taking out all the components that are colored black. All right, so if you look at this one, if you take out all the components that are colored black, you just deleted the whole graph except for some constants. And it does nothing, which is exactly what you'd expect. If the counter is sitting there and you give it no input, you expect it to not do anything. So this represents how you modify this graph when you see no inputs. Let's take the count signal. The count signal says if you see a count and this count signal is true, this example handles an up-down counter. So the count signal is a Boolean. It's true if you want to count up. It's false if you, or no. Oh, no, sorry. This is not the up-down counter. This is a non-volatile read. So the count signal is present and true. It means you want to count up. If it's present and false, then it's just a non-volatile read. OK, so if the count signal is present and true, you have a constraint here saying that you can only apply this mode if the count signal is true. Then you delete this from the graph. You delete this from the graph. And all you're left with is a path from the adder to the output. And then you get an update of the signal. Okay? So you can see it's sort of like in classical digital design. You design a control, you design a data path, and you design a controller on top of it. But in this partitioning, each one of these has a very precise semantics. Synchronous data flow graph and a set of modes. There's very precise semantics about when you apply a mode and the sorts of conditions it can have. And it allows you to reconstruct a synchronous model in a model-based way by partitioning it this way. You can simulate this with or without the controller. If you simulated this counter without this controller, just using the synchronous data flow semantics, you'd see some non-determinism where these signals are merged together. When you apply the controller, this non-determinism goes away, and you get exactly what you'd expect, which is this counter. And this makes the links between the different levels clear. The modes depend on the structure of the graph. Also, the values calculated in the graph can be used as conditions on the modes. And the modes affect the graph in a simple way. It removes an operator. It reconfigures. Okay? It turns out that when you split a system up into this way, you can actually design conservative approximations of all these very difficult global properties. You can conservatively approximate causality. You can conservatively approximate inconsistent sets of equations using a simple type lattice. I think I won't go into all of this, but basically, as the designer builds a system and says which operator should be present or absent, you click a button, it does some type analysis on this graph, and it can tell you if it finds any errors. It can do this in polynomial time. The only caveat is that it's a conservative approximation. It might give you false positives. And I should note that this conservative approximation, you couldn't get it if you didn't partition the system this way. The key here is that you're able to break up these clock equations into these individual control responses. Okay, so then I went ahead and I implemented this in our tool suite GME. So what I do is I developed a set of meta models that precisely characterize the structure. And then I develop a set of components that sit on top of the model traversal libraries of GME to make all of this happen. There's a component for auto-generating the modes from the data flow graphs. There's a component for conservatively approximating correctness. There's a component that helps you keep track of everything you've built. And there's a simulator. So I don't know, how much time should I? Okay, so I'm going to run through this pretty quickly. I just want to show you that you can go from this theory into a tool pretty quickly now using the model-based approach. So to begin with, you need to define a meta model for these basic operators. And this is pretty simple. It says that an operator contains some ports. Ports have data types. They have vectors. You can describe if it's a vector type. And then you can, so you describe this meta model. You feed it into GME, and then out pops your modeling environment. You can now build libraries of these basic data flow operators. And then there's ways to connect these data flow operators to simulators. So you can say on the structure that if you simulate me, I'm a class OR. I'm an instance of some class OR that's defined externally to the modeling tool. Okay, now you need to be able to connect these into data flow graphs. So you build another meta model that says that a data flow graph contains operators, and that these operators can be connected together by data flow connections. And also a data flow graph can contain components which themselves contain data flow graphs and modes and all of this stuff. So you have hierarchical composition. Now you can build something simple. Oh, I should say I'm using this DSP example just because I think it's a familiar example. There's no reason these have to be AND gates at all. These can be anything. So this example, you can say, let's say you wanted to build a plus, a 2-bit adder. You would take these basic operators and link them together in something like this. Okay, then you build another meta model for the modes. And the modes are linked to the operators in GME by a reference. It says that a mode operator is something that refers to an operator in the underlying data flow graph. You build this meta model, and then you get a tool for constructing modes on top of data flow graphs. Okay, so very rapidly you can see that the structure can be evolved. Now, modes also support hierarchical composition. So the question is that if you take a component that has all of these layerings in it, and you put it inside of a single mode, a single control response, what does that mean? So for example, this 2-bit adder had 2 control responses. You give it no data, it will give you no data. If you give it all of its data, it will give you all the data you want out. And anything in between is illegal. If I embed this adder into a bigger 1-bit ALU, the modeling tool will actually approximate which of these modes would be chosen in this particular control response and project this type information up onto the ports. This is not done automatically. I had to, of course, write a tool to do this. But more or less, it can be prototyped pretty quickly. On top of this, again, is a tool that watches your actions as you build the data flow graph and modifies all of the modes that you've previously created. So this one, again, is a 1-bit ALU. Each of these modes says for a particular opcode what ALU response do you want, and it tells you how to reconfigure this underlying graph to accomplish that response. If you make any modifications here, let's say you add a new component, all of your actions are monitored and reflected through this whole data flow graph, so that link is correctly maintained. The conservative approximations can be invoked by a mouse click. You recalculate the interfaces, and it will apply this through your graph. In color code any mistakes it finds and gives you a list of all of those errors. And I should say this is actually really useful, because if you ever used any other synchronous reactive environment, the only way you check your design is by compiling it through this intractable process. So you really can't do it that often. You get a big design, and you have to wait a while. Because the algorithms have exponential complexity. The implementation of the algorithms have exponential complexity. So here you can actually just make a change. You click a button, and you get a pretty good idea about if you've made any behavioral mistakes. There are some extensions to this that I'll just mention really quickly. I said that a mode has the ability to delete things from a data flow graph. If you have a set of modes now, you can imagine going one step further and having a structure that can dynamically change which modes are available. And this is an interesting extension. It's essentially an automaton that which state it's in tells you which subset of modes you're allowed to apply. And this can be used to encode some advanced features in synchronous reactive languages. Really what it's good for is encoding state-based protocols. So you can abstract out the essential state in some protocol into an automaton like this, and actually apply some interesting analysis, interface automata analysis, on top of these. And then a final extension was to also provide a platform deployment language where you can take your model and you can say how the components of this model are distributed across platforms. We have a summer internship program funded by the NSF, and the students here use this to take a robot controller and to put some parts of the controller in a robot, other parts on a PC, and then correctly link the two so they could deploy these things in heterogeneous ways. And then you can simulate, you get some pretty scopes and that sort of stuff. So the conclusion is that modern systems, they have this heterogeneity, they're distributed, they coordinate through a complex environment, and that they have many interacting requirements. Model-based approach offers one way to sort of mitigate, to amortize this complexity by spreading it across domain-specific languages, spreading it across platform stacks. And in a case study where we really took an example of a fairly complicated language and really dug into it, we found, yes, you can really apply these model-based approaches, and you can get modeling tools that really have an advantage over not using the approaches. These are both in the formal sense that you get conservative approximations, and in the user sense that as you design, you can check, you can think in different views. Now, I just want to point to the ongoing work now is to think about this model-based approach in a more formal way. That is, to try to find formal methods that really capture what's going on. Why does this work? Why does this divide and conquer approach work? And I've been looking into different areas. The one that I think is fairly well completed is the structural semantics, so that from a meta model, you can extract a formal definition of all of the structures, all of the well-formed structures that belong to your modeling language. You can apply formal methods on these structures. You can try to find a structure with such and such property. An automated theorem prover can find the existence of such a structure and can construct it if it exists. Then that applies the structural part. Ongoing work, too, is now to link the structure and the behavior in an interesting way. So to be a little technical, you can view the structure and the behavior as actually sorts of lattices, and you can look at what happens if there exists certain homomorphism between these lattices. What's interesting is if it's an order homomorphism. And it turns out that in some interesting cases it is. And a longer-term work that's been sort of going on and off for the last year is to try to find some other ways to describe semantics that are more geared towards composition of semantic domains. One interesting approach is a multilinear algebra approach that would leverage the theoretical foundations of linear algebra, which has worked very nicely in other fields, but extend it to the sorts of domain-specific semantics that you find. This is a longer-term thing. So thank you. I'm sorry if I took too long. I'd love any questions.